Hello, everybody. It's Professor Rehse again. So pleased to be joining you for yet another fabulous and fantastic DoD STEM K-12 Saturday. I am talking to you in January of 2025, and we are conducting today our Nchiiwad, Tormenta de Nieve, Snowstorm K-12 Saturday. That's Nchiiwad, which is Ojibwe for snowstorm. Tormenta de Nieve, as sorry for my Spanish, is Spanish for snowstorm, and of course English snowstorm, representing the cultures that we are bringing together in this joint Saturday STEM K-12 seminar series. So as always, very pleased for you to be joining us. Very pleased to be invited to talk to you today. Have another great topic that's relevant to the cold and blustery January we've been having here in Windsor, Ontario, and our with our good friends Detroit, Michigan, right across the river. So let's see if we can go ahead and jump right into this blustery topic and see if you can see what the relevance is to my topic today with what's going on with the weather outside. So I'm going to share my screen here so you can see that today's lecture topic is going to be on the power of crystals with that word power kind of what do you call it in quotes up here. That's kind of going to be what I'm talking about, which is what do we mean by when we say crystals have some power? Let's dive into that today. So again, as always, my name is Professor Steve Rehse. I'm a professor of physics and the head of the Department of Physics at the University of Windsor. Very pleased to be participating in these monthly STEM talks that I hope more of you find out about and choose to join us. They are targeted at school-age children. Anywhere between grades 6 and 9 would be appropriate for this series of talks. So we really do hope you look into this and try to join us if you can. Here's Windsor, Ontario. So I hope some of you from all over the world are watching us, and you can see what close partners Windsor and Ontario, Canada, and Detroit, Michigan, United States are, separated by a small body of water, the Detroit River. Really sister cities in all senses of the word. And the University of Windsor is located approximately where this star is. The University of Windsor actually sits on the traditional territory of the Three Fires Confederacy of First Nations. This includes the Ojibwe, the Ottawa, and the Potawatomi. So we respect the long-standing relationships with the First Nations people in this place, and the 100-mile Windsor-Essex Peninsula and the Straits are Le Detroit of Detroit. Then you can see why this strong partnership between the people of Detroit, the people of Canada, the First Nations people in this area makes this STEM Talk series such a unique opportunity for the residents. So let's go ahead and dive into it. So we're talking about the powers of crystals today. So let me just start by, trying to summarize or ask you, what is it that most people know about crystals? I think most people know the word crystal. Most people know of crystals, but if I ask you, what are they really? Can we define that? Let's see if we can do that. Then more importantly, what powers do people think crystals have? There's a lot of information and a lot of stories out there about what powers crystals might have. What are those? And then what powers do crystals really have? And that's as a scientist, I'm going to try to convince you that the powers that crystals really have is actually really more incredible than the powers that people think crystals have. So let's just define this. What is a crystal? If you know the word, but what is it? So a crystal is a solid or liquid with a very ordered and repetitive arrangement of atoms, ions, or molecules. A good example is just this generic wallpaper that I have on the back of my PowerPoint here. So you see this kind of lattice structure. This is showing a hexagon of 1, 2, 3, 4, 5, 6 atoms, and they kind of repeat over and over and over. That pattern of hexagon shape, that's 6 atoms, over and over and over. That very regular arrangement or repetition is what defines a crystal structure, and all the properties of the crystal are going to come from this very repetitive and periodic arrangement of the things that make up the crystal. And those things could be atoms, ions, or molecules that make up that crystal structure. So one classic example that I'd like to give you, and at least just start with, is right here. I'm showing it here. It's table salt, right? Good old NaCl table salt. And of course, because I live in Windsor, Ontario, Canada, I am showing you the type of salt that we eat here, which is Windsor brand salt. It is actually mined right here in Windsor, dug up from under the ground. Now, when they dig salt out of a salt mine, it does not look like this white powder, which is what you sprinkle on all of your food. It looks more like this. So this is rock salt. So if you've ever heard that phrase rock salt, or if you have big salt crystals that you're in the salt grinder that grind up, this is what it looks like when it gets dug out of the ground. This looks like a crystal. If you have some image in your head of what a crystal is, this starts to look like a crystal, right? Because it is. Sodium chloride that makes up cooking salt, table salt, is actually a crystalline material. And so if I had a super duper physicist microscope and I could zoom into that rock crystal, what would I see? Because it's a crystal, I have to see a regular, periodic, repetitive arrangement of something. And what I would see is something that looks like down here, without the colors, of course. I would see a regular arrangement of sodium atoms, which I'm showing here in green, and chlorine atoms, which I'm showing here in purple. That's why salt is NaCl, sodium chloride, but it's not just sodium and chloride mixed all together. It's in this very regular arrangement. So you can see this very periodic arrangement of green, purple, green, purple, green, purple, and it goes on forever. And the purple looks like it's arranged itself in diagonal lines. These would be sheets of chlorine atoms that run through the material. It's that regular arrangement of the sodium and chlorine atoms that make this NaCl a crystal. And so that's actually just a really good example of it. So that's just one example of table salt. Now let's talk about what are other types of crystals that you might be familiar with. Because if we've defined a crystal as a solid or liquid with its ordered and repetitive arrangement, the thing, whatever it is that repeats itself over and over again, can be almost anything. So crystal is generic. Crystal defines the structure of the thing, but what is the thing that repeats itself regularly? That can be almost anything. So let's explore what some of those things could be. So say, for example, that thing is just the carbon atom, one of the most common atoms on all of the earth. So what happens when you make a solid and it's just a repeating pattern of carbon atoms over and over? You're going to get something that I bet all of you know about sitting at home, and that's, for example, diamond. It's not the only thing that can result from a regular arrangement of carbon, but the diamond gem is a crystal. So if you dig a diamond out of the earth, and they do mine diamonds, we have man-made diamonds as well, I'll talk about in a little bit, but the diamonds that are mined out of the earth when they come out, they might look something like this. This is a natural diamond crystal. It is a regular arrangement of carbon atoms. Now, when you think about diamonds, you might be thinking about something that looks more like this. It's a gemstone quality crystal. When it was dug out of the earth, it probably looked like this. You have experts who have a lot of time and a lot of training to learn how to cut that crystal along its regular arrangements or faces to make it look beautiful like that. But the crystal arrangement was provided by nature. The jeweler is just cleaving it along particular faces, which get or facets, which give it this look. And again, if I could zoom in with my super duper physicist microscope and actually see how those carbons are arranged, it might look something like this. So I'm just showing two animations of the particular arrangement of carbon atoms that give diamond its beautiful properties. And so I'm showing the blue carbon atoms here, and then I have these orange pyramids superimposed on top, just so you can see that they're always kind of arranged in this pyramid form with one carbon atom at the middle. And that's the fundamental unit. And then the crystal just repeats that an infinite number of times into this large solid that you can then see. What else do we know? Okay, how about this one? So what is that thing that repeats itself over and over? What if that thing that repeats itself over and over again is just a water molecule? One of the most common molecules on all of the Earth. What happens then? Well, if it arranges itself into a regular, ordered, and repetitive arrangement, that could be a snowflake. A snowflake is a solid for sure, but it is a regular arrangement of water molecules. And so here are two beautiful photographs of a snowflake. If you zoom in, and you can clearly see the crystalline structure of these objects. And again, if I take my fancy super duper physicist microscope and zoom in and see how are water molecules arranged in a snowflake, here is how the water molecules are arranged. So I'm showing the hydrogen atoms in these little red dots, and the oxygen atom is this big blue dot. And you can see that it does form this kind of, again, six-sided hexagonal structure. So within this snowflake, which we don't see, there is this hexagonal or six six-sided arrangement of atoms, and it can form a simple hexagonal prism or a plate or a column. And so there's lots of ways that there's lots of different shapes of hexagons in these snowflakes, which is why there are so many different ways that the snowflakes can present, but it's all based on the six-sided arrangement of water molecules. Solid water molecules make a crystal snowflake. Here's a one that you might not have thought of, but I bet you use the word at least once a week. What if the thing that repeats itself over and over again is a long molecule? A long molecule whose name is unimportant. And if I then put those long molecules and arrange them next to each other such that it's still a liquid, the water molecules are not bonded to each other. It's still a fluid, it's still a liquid, but it maintains that order through the liquid. What happens then? Well, when you make such a material, that's called a liquid crystal. And there are liquid crystals, not nearly as many as there are solid crystals, but liquid crystals are a real thing, obviously. So as in regular liquids like water or gasoline or milk or something like that, as in regular liquids, the molecules can flow past one another. So it is a fluid, but also, as in solid crystals, the molecules within the fluid that can all move arrange themselves in recognizable ordered patterns, and that's what makes it a crystal. It's a liquid because the thing is not a solid and the molecules can flow past each other, but as in a regular crystal, there has to be this regular periodic arrangement of those long liquid crystals. And of course, what that's important for is the liquid crystal display, or LCD. I will bet almost anything, if you're watching me right now give this presentation, you're watching on your phone, you're watching on a laptop, you're watching on a computer monitor, you are watching me through an LCD, liquid crystal display. That is one of the most obvious forms of crystals that is ubiquitous because we're looking at each other through crystals right now. A weird form of crystal, liquid crystal, but a crystal nonetheless. Let's think about that water molecule again, the lowly water molecule. So water molecule is an oxygen and two hydrogens kind of vibrating around like that. And we've already said that water, as you all know, go get yourself a glass of water and drink it. It's refreshing. It's a fluid. It's a liquid, of course. Then as you cool these things down and that liquid wants to solidify, it becomes a solid. And as those water molecules solidify to become a solid, if they arrange themselves in this regular periodic arrangement, it can become a snowflake, which is solid water because it's a solid and it's a crystal. But it doesn't have to, of course, because when you put ice in an ice tray and put it in the water in an ice tray and put it in the freezer, it forms another form of solid water, which we call ice. So snow is solid water and ice is solid water. This is a crystal. This is not. So what's very important to take away from this is that not everything is a crystal. In fact, most things are not crystals. So if you go outside or just look around your house, whatever you want, take any of the solids in your house, in your room, in your yard, whatever. Things like concrete, steel, wood, glass, whatever. Most things are not crystals. None of those things are crystals at all. They are solid, yes, but not crystalline at all. So crystals are a subset of the solids, and that makes them very, very special. It's actually a small subset. The vast majority of things are not crystalline. So crystals are really special. What's so special about them? Well, they're going to have special properties. And one of the most important properties of these crystals is because they are arranged very regularly, when those atoms try to move, they are not free to move as they want. Think about 1,000 of you or 100 of you packed into a gymnasium and you're all kind of standing next to each other. Because of the arrangement of you, people are not free to move about and run about or dance about kind of willy-nilly. There's a very controlled movement. And I'm showing that in these animations here on the left and the right and in the middle where I have this purple atom and it's like connected by these springs to all these other atoms. Because of this web of connections, this network of connections from this regular periodic arrangement of things, the way these atoms can move or vibrate is highly constrained. They tend to vibrate at very specific, extremely well known and calculable, very predictable rates of motion. We call that the frequency of motion. And that is unique to these crystals. And the thing about these vibrations, these oscillations, is that vibrations are energy. That is true. When these atoms are moving back and forth, that is the energy in the crystal. It could be thermal energy or other sorts of excitations, but that vibration, that moving back and forth, is the energy contained within the crystal. And that means that the energies contained within these crystals are very, very specific, specific to that crystal. Now, here's where things get a little complicated because unfortunately, many people believe that these vibrations that are unique to a crystal, that energy that's associated with those specific vibrations can give these crystals mystical or magical powers. And I'm showing some different ways of how people think about how crystals have these powers. So I looked into this a little bit and I want to say, well, what powers do people actually think crystals have? So I found this quote that says, people use healing crystals because they believe these stones have natural energies that can positively impact their lives. And note this is a quote, and I did underline the word believe, and that is true. People use them because they believe they have these natural energies. And the belief in something can be very, very powerful. And so what is it that people believe the crystal can do for them? Well, there's a lot of different things that people think crystals can do for them. They believe that crystals can restore your balance and a sense of calm. They believe that crystals can focus your mind and give you clarity of thought. They believe they can boost your energy and your vitality. They can give you a spiritual connection to the universe or to others. They can create conditions of emotional healing where your mental health can improve. They believe that they can actually interact with your physical tissues and generate physical healing. They believe that they can boost your confidence and your self-esteem in yourself, boost your creativity, make you more productive. They definitely believe they can attract prosperity. As you start to use and interact with these crystals, wealth can come your way. Perhaps it'll boost your motivation and make you work a little harder, reduce the stress in your world. There's a lot of things that crystals can do. In fact, one of the most powerful, it is claimed, crystals is this quartz. And so here's some pictures of these beautiful large quartz crystals. And I found this quote that says, quartz is the master healing stone and is possibly one of the single most powerful crystals we can think of. It's famous for its ability to suppress negativity and promote optimism and peace. That's a lot of work for one crystal to do, considering a quartz crystal is basically just a chunk of rock where the atoms and molecules have arranged themselves very, very regularly. So poor quartz has a lot of work cut out for it if it really has to do all of these things. So these are just an example of the things that people who sell crystals or utilize crystals believe that the crystals can do for them. Uh, Unfortunately, none of any of that is true from the scientific point of view. You're free to believe what you want, but as a scientist, belief in something is not how science is done. This is a STEM talk: science, technology, engineering, and math. Science must concern itself with what is provable, what is quantifiable, what is explained with theory or predicted with theory, and none of those phenomena associated with crystals have ever been observed or will be observed, because that's really not what crystals do. So none of those beliefs are true, and the crystals do not interact with your physical tissues in any way, and they don't interact with cosmic energies to bring you wealth and prosperity. It just does not work that way, I'm sorry to say. But that's not the end of the story, because as a scientist, I always have a better version of reality. And that's what I've always found as I've dug further into science, is that the truth of science is usually way more interesting and fascinating than all of these other belief systems or imaginations of how the universe works. The truth of the science is actually usually cooler than that, because I do believe that these crystals do have real and very useful powers, because crystals are extremely useful and utilized in our technological society. I'm just going to give you a couple short examples. There are hundreds of examples, and I just wanted to give you a couple just to give you some idea. So the first one I thought of was radios. So this is an so this doesn't look like any radio you guys have ever seen. This is an old radio set, but back in the day, back maybe in the 30s, they used to call these a crystal set. There's a crystal radio receiver. People used to say they just get on the crystal set. And I remember when I was a boy, I was always wondering, what do they call it? Why a crystal set? Why do they call it that? It's a simple radio receiver, very popular in the early days of radio. It uses only the power of the received radio signal to produce a sound, needing no external power. And it's named for its most important component, a crystal detector, originally made from a piece of crystalline mineral such as galena. So this is just an example of what galena looks like. Not a big chunk of this rock would not be inside this. It would be a portion of that galena crystal, cut down, polished to be the right size. But that crystal gives this detector, this radio wave detector, its ability to differentiate the radio waves at these different frequencies, making this thing a very useful tool and one that does not require power. So a very interesting set. And crystals were first used to detect radio waves in 1894 by Jagadish Bose. So this is well over 100-year-old technology, and so people are recognizing the utility of crystals. And for the older people in the audience, like myself, maybe someone who grew up in the 70s, or maybe somebody who had children in the 70s, you might remember this picture, which will bring back a blast from the past. So this is a 1970s era Aero crystal radio marketed to children. This is a kid's toy. So long before the age of the internet for you younger people on the call, before we had the internet, before we had cable TV and things like that, people were interested and getting interested in STEM science fields in a variety of different ways. And one of the ways was getting involved in circuitry and radios right away. So this is a crystal radio set. It's called the Aero Germanium radio. So I'm assuming that means that germanium, which is one of the elements on the periodic table, is the crystal that they're using inside, a germanium crystal. And you can see here's a very primitive earpiece. So before you guys had earbuds, this is what an earpiece looked like. This is for connecting to an antenna, maybe some power source or something like that. I'm not exactly sure. But you can see the plastic marketed towards kids, and young people got really introduced to science by working on engines and building things like radios and things like this. And this is how people started to see, oh, science is really relevant to my life, and even useful for toys and objects marketed towards children. Another very important power that crystals can give is its use in watches. So you may have heard of a quartz clock or a quartz watch. I wanted to talk about that because when I was young, I always used to see these watches that had the word quartz on it. And I was wondering, what does that quartz mean? It's like, I always thought that because quartz, these crystals have energy, that is actually what was powering the watch. That's not true at all. So if you're talking about a quartz watch, which is what I'll talk about, it's a timepiece that uses an electronic oscillator powered by something else, but it uses an electronic oscillator, which is something that varies back and forth electronically, regulated by a quartz crystal to keep the time. So this crystal or quartz oscillator creates a signal with a very precise frequency. The piece of quartz they use vibrates back and forth at a very, very precise frequency. And they use that to help keep the time. And that in that way, quartz clocks, quartz watches are at least 10 times more accurate than mechanical clocks. A mechanical clock maybe just has some gears going together, and that's what kind of keeps the time. But the atoms of the quartz vibrate on a way more precise frequency than that. So here are two inner pieces of a watch. The quartz oscillator would be this thing right here. And in the zoom up right here, it's this thing right here. So you're seeing a lot of, it looks like loops of wire, coils of wire, and the quartz crystal would be embedded inside there. In this picture, the quartz crystal is embedded inside this thing. It is the timekeeper of the watch. It is not a power source. These watches will still have a battery that powers things, right? But it needs some power. It needs the quartz crystal to keep the time. It's the thing that makes the tick, tick, tick stay on a very regular pattern. And because this quartz is so much better than mechanical gears, quartz watches can actually be quite expensive. I'm showing you some of the luxury brands. And so, for example, a Bulova watch, and here it says quartz water resistant. So if you ever wondered why it says quartz, does it mean that the face, the glass that protects it is quartz? No, it means it has a quartz crystal embedded in it, and that's helping it keep very accurate time. Here's a Citizen watch, again, the quartz WR50 watch, again, pretty expensive watch, quartz timekeeping inside. And because I'm a very proud resident of Windsor, Essex County, neighbor of Detroit, we want to give a shout out to one of the best watch brands in the country. This is the Shinola watch. It's made, manufactured, produced right in downtown Detroit, right across the river from where I'm recording this video. And these Shinola watches, you can see here, it doesn't say quartz on the front. Their watches say Argonite 705. And I believe that Argonite is the form of crystal. It's the name for the type of crystal that they use embedded in the watch mechanism to help it keep accurate time. And again, here's just another interior of one of these watches. And you would see here's a small battery, and here would be the quartz timekeeping piece inside, all embedded within this watch face, keeping accurate time. Crystals make lasers. I'm a laser physicist by trade. Crystals are extremely important. So if you've ever seen a powerful laser industrial or maybe a laser pointer, you might have a crystal head that looks like this. There's some kind of diode laser that's creating the light source, but then there's these two crystals. This is called a neodymium yttrium vanadate crystal right here and a KTP crystal right here, just solid chunks of gem quality but man-made crystal that can then generate the laser light that you're using to project on the wall. So very special properties of crystals that allow a very specific light to be generated. Laser diodes are extremely common. They're extremely small, although most of you may have seen the light from a laser diode. I bet you've never actually seen a laser diode. They're incredibly small. Here's a US penny for scale, and here's the laser diode in its can for scale. This is so what? This is about a fifth the size of a penny, but the laser diode is way smaller than that. If I cut off this metal outer coating, which we call the can, and if you could look inside of this thing, so here's the laser diode assembly, cut that can off, it would look like this. The laser itself is this thing inside. So how small is that? These things are about the size of a grain of sand. Honestly, if you've ever held sand in your hand and try to isolate just one grain on the end of your fingertip, that's the size of this crystal. In this case, it's an aluminum gallium arsenide crystal. That crystal is the laser. That is the amazing power of a crystal. That something the small of a size of grain in sand can create this incredibly intense light source that then you can beam across the wall, that can be used to read CDs, DVDs, used in your computers, everything like that. That is a real power. Uh, Here's one other application, which is in medical applications, ultrasound. So ultrasound is commonly used in many medical applications to look inside the body. I'm showing the application here where it's used. They're looking at a developing fetus. So they're looking into the womb, and the ultrasound works by producing sound waves that project outward from the end of this object that the technician is holding. It's called a transducer. Here's the schematic of the transducer right here. It produces sound waves which shoot into the patient, and then those sound waves bounce off things and the echo is returned. And then that gives you the image of the thing you're trying to image. And what is it that generates these sound waves? Well, it's the regular vibration of something called piezoelectric crystals. And that's shown right here in the schematic of the transducer. Very special types of crystals. They vibrate back and forth at a very precise frequency. And that's what creates this ultrasound or high frequency wave. You could not have ultrasound technology without crystals. Would not be possible. And then I think the last application I have for you is in drilling, cutting, and grinding. So one great example is, again, diamond. So we'll go back to the diamond gemstone that I showed you at the beginning. Digging diamonds as gemstones out of the earth isn't the only way we have diamonds. Humans are very good at manufacturing what we call man-made diamonds now. And because we can grow them and make them ourselves, not of gem quality, but it's still, gem quality just means it looks beautiful. We are very good at making diamonds have the exact same crystal structure and have all the same properties of diamond. They just don't look pretty. And when we make those diamonds, we use them for industrial purposes because diamonds are the hardest naturally occurring substance found on Earth. Makes it very useful. What does having the hardest substance known on Earth get you? Well, you can use it in something called a nano indenter, which is used to measure the hardness of other materials. So this is just the nano indenter is just a machine that has a diamond kind of added at the end of it, and then you push this thing into the other material. And because diamond is the hardest thing, it will push into everything else. It has to. If you have one thing pushing into another thing, the harder thing always pushes into the softer thing. And since everything is softer than diamond, when you push in this nano indenter, it will make a small mark or indentation in the material. And then the depth or size of that indentation will tell you how hard the material you were pressing into was. So very useful industrial application. And then here again are some examples of drill bits. So when you are drilling into the earth, so this is a drill right here. We're seeing the business end of a drill. It's going underground. What is it that you use to cut into the ground, into the stone, into everything down there? Well, these are different diamond coated drills. This would be at the end of this thing, and these guys rotate. And because, again, diamond is the hardest thing, in theory, it will cut through anything. There's nothing on Earth, naturally occurring, that's harder than diamond, which means it can cut through anything. It will wear away for sure. So they're not infinite because there is wear and tear, but in theory, it can cut through any stone that it encounters. And these are large industrial drills. These are just Dremel. If you Google this, these things are like a couple dollars. So these are Dremel tool bits, grinding burrs that you would use for a handheld tool, and it's man-made diamond impregnated on all of these tool heads to allow you to kind of grind away any material that you want, because diamond is the hardest material. So very useful, a very magical and special property used for drilling, cutting, and grinding. Very useful to us. That's just a couple applications. As I said, there are hundreds of applications, but I don't want to go on and on. I think I've given you some insight that all of those cool applications that I've listed really do make crystals pretty magical. They are pretty special and unique forms of materials on our Earth, and we are able to exploit and utilize those special properties to do really cool, interesting, and again, magical things. And I hope you would see it that way as well. So I think crystals really are kind of magic, but just not in the way that most people mean when they say crystals are magic. So with that, I would like to conclude my talk, say thank you all very much for joining us today. I hope you've learned something about crystals. I hope you'll join us again in the future. And as I wind up this talk, maybe I will leave you with maybe something that Yoda would say after giving you such a presentation. May the quartz be with you. So thanks, everybody. I appreciate your time today. Um, look forward to talking with you again. Uh, if you have any other thoughts, you can maybe leave them in the description of this video. Please check out all the other different recordings that I have here. And again, if you're really interested in any of these STEM K-12 DoD talks that I have listed on my YouTube channel here, please check us out. If you kind of Google that or look for it in YouTube, you will see some promotional videos for it, and hope that you'll be able to join us at some time. It's a really great opportunity. It's a really great community of people who are just really interested in passing on our love and passion for the STEM field to the next generation of what I know are going to be absolutely fantastic scientists and engineers. And it all starts right here. So thank you so much for you guys for watching these videos and engaging with us. I enjoy it. I hope you did too. I will talk to you real soon. Thanks a lot.